So in this demo, we will go over some of the things that we discussed in the videos before. So this is the logistic regression demo. As we discussed in the previous videos, logistic regression can be used for classification of data. So in this notebook, we'll discuss this logistic regression, how we implement this for a data set that we create. So here are a bunch of libraries that we need to have this implemented. We need NumPy for data arrays. We need matplotlib for plotting. We need time for timing things. We need the classifications data sets for creating classifications data with certain classifications. Then we have a train and test split, which allows us to divide the data set into a training set and a test set. And then we have one hot encoder, which allows us to label the categorical data with numbers or vectors of numbers. And then we have the accuracy score that allows us to see how good the model is. So let's run this. First of all, I'm just going to initialize this so that it doesn't have anything left over. So the first thing you do is just initialize those libraries. So now we are ready to use them. And so the first thing we do is that we're going to use this make classification library to create a data set with 3 categories and 300 samples and 2 features. In other words, we're going to try to divide these 300 samples into 3 categories, and each data point has 2 features. So in this case, we're going to use a synthetic data set. So we are trying to create a synthetic data set using make classification library. So each class is modeled with a single Gaussian cluster, making the class boundaries clearer so that there are no intersection across boundaries. So we call the function with 300 samples. We want 2 features in each of the data points. And also we need 3 classes. And we only need 1 cluster per class, so that classes are very well defined by some classification, say 1 or 2 or 3. We use the random state 42 to make sure that it ensures reproducibility of this code that when we run this again. Then we're going to be doing one hot encoder, which means that if you have categorical data, then they will have to be encoded as vectors, in the sense that, let's say you have 3 categories. So you have a vector of size 3 with one of the entries being 1 and the other 2 being 0. So this means only 1 category per observation. So let's run this, and then it creates the encoded. So if you want to look at the encoded data using one hot encoding, we can look at this. Oops, I spelled it, so let's just do this one here. So you can see that this is the one hot encoding of the data. So this indicates that the first data point is the category 2, the second one is category 3, third one is category 3, and so on. So that's that. And then the next thing that we need to do to see if this is a good data set, especially if you're getting a data set from the real world, you have to see if it's a good test for classification using logistic regression. So the next thing we're going to do is we're going to take these 300 data points and we're going to divide this into training and a test set. And the test size would be like 30% of the entire data set, and the training set would be, in this case, would be 70%. So now the first thing you want to do is just plot the points to make sure that this is something that is probably good for logistic regression. So we will look at the minimum of the data set and the maximum of the data set. And then we will create a grid which will plot using xmin, xmax, ymin, and ymax. So now the next thing we're going to do is we're going to do a scatter plot of X first feature and the second one. And we're going to take the color coding. So for example, we're going to use the Coolworm color map, which assigns distinct colors to different class values for better visualization, and sets the edge color for each dot to black by saying edge color K. Those are optional. Then we label the X as to be feature 1, Y axis to be feature 2, and so on. So let's take a look at how they look like once we plot it. So once we plotted these data points that we have, these are two-dimensional data points, you can see that they are distributed, but they are kind of clustered clearly in this space. So the idea is to figure out what the separation lines are in this case. So that's going to be the focus of our logistic regression. Now, as you saw in the previous video, we used the sigmoid activation function. So what that does is to take a real value coming from the linear regression and map it to a value between 0 and 1. And the softmax, also another option where you can use to use as a activation function. Let's initialize these activation functions. And now we have to initialize weights and bias. As you know, the linear regression has the form y equals wx plus b, where w are the weights matrix and the b is the intercept matrix or the bias matrix. So basically what we're going to do is we're going to take the shape of the x, which is going to give us the how many things we need, and then we have n classes, and then we create this W matrix to be these are the weights, and they're going to be zeros and n features and in classes. So B would be it's a vector which has one row and n classes, n columns. So let's initialize that. And now to the training function. So let's take a look at the training function. So what the training function does is to perform the gradient descent algorithm. You can watch the video on gradient descent if you missed the idea. Optimize the weights W and biases B for the logistic regression model. So basically we are writing this training function which takes the original data set X and your labels Y and the weight matrix W and the B vector. And then we run 1000 epochs, which is running through the same data set 1000 times. So here we take the dot product. This is like X transpose W or W X transpose plus B. This is a vector you get. And then in this case, I'm using the sigmoid function applied to bring the numbers between 0 and 1. And the loss is going to be the difference between the actual weights and the actual values and the predicted values. So we do sum up all the total loss by taking this, and then we add this small number here to make sure that the log, if the probs are 0, it won't crash. Axis 1 means the number of columns, so you go add them by the columns. So then we compute the gradient. Again, watch the gradient descent algorithm to see how the gradient is computed. And then we look at the delta B. So delta W and delta B. And each iteration, it's going to change by a little bit there. And then we update the parameters by multiplying those subtracting the delta W times the LR. Okay, and then whenever the epochs number is a multiple of 100, we're going to print what the loss is, and then we'll sleep for 1 minute just to get a hold of what it is, what it does. So let's initialize the training function, and now let's initialize the predict function. This will be used later, which takes the X and the trained weights W and B and try to compute the probabilities using the sigmoid function again, and then it will look at the class this belongs to. So in training the model, we're going to call this function train, which is what we define here. And the train function will take the training data set X and the training data set for Y, the weights in the W, which are initialized to 0, and then we'll run it through 1000 epochs. So let's see what happens here. At the end, it's going to print the accuracy. So you will see that your loss is quickly reducing from 0.69, 0.31, 0.26, 0.21, and so we arrive at an accuracy of 89%. So this model is as good as 89%, and you can increase. You want the accuracy to be higher. You can try various sizes of data, more than 300. We just train with 300 data set. And so you can, at least this model we know is 89% correct, because it compared the actual labels of the test data set with what the model predicted from the data set there. So now what we want to see is what are the decision boundaries. So this is going to plot the decision boundaries. The only thing that's different is that it's going to plot the axis. So let's see what happens here. So there it is. So it plots the decision boundaries. Now you can see that there are still some things that are not. So this, when you say 89%, the things that are misplaced is that 11%. So these are all fine. They are all in the right category, but these things are misplaced. And there are some other things misplaced. So these red ones are misplaced. These blue ones are misplaced. So we are saying it's like 11% of the data set. So that's the basic idea of logistic regression. And to practice this, you can see the comment section to see how to access this file.